Here, when we say linear control, we are talking about typically the word linear comes from the fact that the system is linear. That is, it will only depend on the state, not the square of the state or cube or anything which drives it away from being linear. That is linear in state, and also it's linear in control. So when you have a controller, the controller is more or less when the controller is doubled, the state system, something about the state is doubled. It's not like when the control is doubled, the state is quadrupled or something like that. So it's just everything is linear. And before we do linear control, we have to understand what state space representation is. So that's where we're going to get to. So I'll illustrate state space using a simple spring mass damper system. Spring mass damper system may not look like robotics, but it turns out that many suspension systems are actually spring mass dampers, and there are ways in which you can design the suspension system based on simple models like this. So there are two masses, M1, M2, and there are two spring constants, K1, K2. The left side there's a wall. I'm going to indicate a control. In this case, the control is going to be a force. Let's say that this control is U2 on mass M2. And then there's another control, which is U1, but the way it acts is it not only forces M1 to move to the, well, it pushes M1 to the left and M2 to the right when it is actuated. So in this case, U1, U2 would come from linear motors, things which move in straight lines as opposed to moving in circles. Now this system can be modeled by two variables. Let's call them Q1 and Q2, where Q1 and Q2 are the positions of those masses. So let me now define all the quantities I talked about. M1, M2 are masses, K1, K2 are springs or spring constant. U1, U2 are controls. In this case, they are going to be forces. And Q1, Q2 are mass displacement. Okay, now we'll derive the equations of the system, and it turns out that you can still use the Euler-Lagrange formulation. So we will define the kinetic energy. It's going to be 0.5 M1 Q1 dot square plus, let's keep it this way. And then the potential energy. Now, we've never really talked about springs before in this course. So the spring energy is just like energy due to kinetic energy. It's going to be 0.5 K1 times Q1 square is plus 0.5 K2. Now, the thing about K2 is that one side, it's going to be pushed by Q1 to the right. Another side is going to be pushed by Q2 to the right. And so the net displacement of Q2 is, or K2 is going to be Q1 minus Q2. It doesn't really matter. You can write Q2 minus Q1 or Q1 minus Q2. The equations will come out to be the same. The only thing you cannot do is you cannot write Q1 plus Q2 because you can see clearly Q1 and Q2 are directed towards the right side. Okay, so this is assuming that the spring deflection is 0 when it is free. The rest length is 0. If the rest length is not 0, you'll have to put that rest length in that equation. So if rest length, for example, of spring 1 is not 0, then you put Q1 minus whatever the rest is, Q0, and then you square the whole thing. Okay, now we can define the Lagrangian, which is going to be T minus B. That's 0.5 m1 q1 dot square plus 0.5 m2 q2 dot square plus 0.5 k1 q1 square plus 0.5 k2 q1 minus q2 square. Okay, so now we have that. The Euler-Lagrange equations are given as follows: d dt of partial of TL with respect to Q dot J minus TL PQ J equals the external forces, which are not conservative, like springs or gravity. Okay, so let's do this for, well, we need to put J equals 1 and 2, where it will be Q1 and Q2 for Qs, small Qs. So let's do it for the first, for Q1. D dt, the derivative of L with respect to Q1 dot, we only have the first term, so 0.5 times 2 m1 Q1 dot. Okay, that's all in the first part. Second part, we need to differentiate with respect to Q1, and you see there are two terms. This is the first, this is the second one. So let's take those derivative. It's 0.5 2 times K1 Q1 plus 0.5 2 times K2 Q1 minus Q2. And this should all be equal to the external forces or non-conservative forces. We can see that from this figure that the net force for mass M1 is U1, but the direction of U1 is to the left. And our convention is right side is positive, that's the direction of Q1. So I'll have to put a negative U1. So this can be written as 0 M1 Q1 double dot plus K1 Q1 plus K2 Q1 minus Q2 was minus U1. We'll try to move everything other than Q1 double dot to the right side. If you do that, you'll get minus K1 divided by M1 plus K2 divided by M1 times Q1 plus K2 divided by M1 Q2 minus U1 divided by M1. Okay, let's do the same thing for 2. This will be Q2. So like before, you'll have 2M2 Q2 dot. Okay, and then when you take the derivative with respect to Q2, we see that the first term involving K1 isn't going to contribute because it's times Q1. So only the second term contributes. I need to do 0.5 times 2 times K1. The derivative of Q1 minus Q2, the whole square with respect to Q2 is going to be Q1 minus Q2. And then I need to take the derivative of the term inside the brackets. That's going to be minus 1. So all this should be equal to the external force. And if you look at mass M2, you can see that there are two forces acting on it. There's U1 acting in the direction of Q2, and U2 that acting in the direction opposite to Q2. So it'll be positive U1 to the right and minus U2 because it's on the left. Okay, so we can simplify this. In my notes, I think what I did was yes, I just happen to, doesn't really affect much, but I just happen to use U2 to be in this direction. So not much consequence other than just changing that sign there. So U2 is in the direction shown, just change that. And so what we'll see is that this will be positive because if you see U1 is pushing mass M2 to the right like this, and U2 is also pushing it to the right. So it's positive for both. Okay, so just correct that. And then we can simplify this as 2M2 Q2 double dot, sorry, this is no 2, plus K1 need to reverse direction of Q2 because of the negative sign equals U1 plus U2. And so I'll simplify this as Q2 double dot equals K2 divided by M2 Q1 minus K2 divided by, sorry, K1. No, K2 divided by M2 Q2 plus U1 divided by M1 M2 and then U2 divided by M2. Okay, there's a negative sign on Q2. Is that what is here? Yeah, so it's positive here, but when it goes the other side, it'll be negative. So what we have is equation 1. And then when you simplify this equation, we have equation 2. Okay, so now it's once we have the equations from Euler-Lagrange, now let's look at how to write this in what is known as the state space form, or say state space representation. So I'll define these variables for the state space. X1 would be Q1. So that's same as position of the first link. X2 is Q2, position of second link. X3 would be the velocity of the first link, so Q1 dot. And X4 equals Q2 dot. So velocity of. Okay, next what I need to do is I need to take the derivative of each of these. So X1 dot. So just look at the first line. It says X1 equals Q1, take the derivative equals Q1 dot. But Q1 dot is X3. So what I'm trying to do here is effectively trying to write everything in terms of X's instead of Q's. Then I have X2 dot equals Q2 dot equals X4. X3 dot equals Q1 double dot. But then Q1 double dot is available to me as equation 1. Okay, so I need to substitute the value of Q1 as X1 and Q2 as X2, and that's what I do. And then I'll keep U1 as it is. So this is from 1. Then X4 dot is Q2 double dot, but Q2 double dot is this equation here. So I just substitute the value of Q1 and Q2 as X1, X2. And I have Q2 divided by M 2 times X1 minus K2 divided by M2 times X2 plus U1 divided by M1 plus U2 divided by M2. So this is from 2. Okay, so now we've seen that we've been able to write everything here in terms of x's and not q's. Because next what I'm going to try to do is I'm going to write equation of the spring mass system as a matrix equation. And that's the state space representation. So let's assume that x, capital X, is x1, x2, x3, x4. And so what we're trying to do is trying to write expression for x dot. Okay, so for that, I need to look at these equations. So we have x dot equals x3. And so what we're getting to is we're trying to write a 4 by 4 matrix. Do it this way. I'll rewrite that, but I'm trying to do x dot equals ax plus bu, where you can write this as x1, x2, x3, x4 dot. And then I need to fill in a 4 by 4 matrix, which when multiplied with x1, x2, x3, x4 will give me all those terms involving x's. And then I need to write a P matrix, which when multiplied with my two controls, U1, U2, will give me whatever I have for the u's. And so the way we fill this up is we look at the first equation. It says x1 dot equals x3, and there's no control there. So the first row should give me that equation. So I go here, I see that x3 is row number 3. So in this matrix, I'll have 0, 0, 1, 0. When 1 is multiplied with x3, I have that x3 showing up in the first equation. And there's nothing for the control. Now, how do I figure out these matrices? Well, x is 4 cross 1, x here is 4 cross 1, u is 2 cross 1. So to make A consistent, when it comes to multiplication, it has to be 4 cross 4 and B has to be 4 cross 2. So I'm looking for a 4 cross 4 here and a 4 cross 2. So that's why I need to have two rows, so 2 columns here, should be 0, 0. Next, we look at second line, which says that second row, second equation, x2 dot equals x4. So x4 is here, so it will be 1, and then everything else will be 0. Okay. Then we have this term which multiplies the x1, this term which multiplies the x2, and then note that x3 dot and x4 dot are 0. So what we do here is we write that over here, first part, k1 divided by m1 plus k2 divided by m1. K2 divided by m1, and then 0, 0, because when zeros are multiplied with x3 and x4, we get contributions of those to be 0. And then we need to complete this part, which is saying that I need to multiply u1 with 1 divided by m1. So that would be the first column of that row, which when multiplied with u1 will give me what I need. And then you can continue that for the last one. It will give me k2 divided by m1 minus k2 divided by m1 into 0, 0. And then here will be 1 divided by m2, 1 divided by m2. So this equation is the state space equation. Okay, it tells you how the system evolves, that is how x evolves for a given u, and your x1 would be when you integrate this, you'll probably do some kind of numerical method, which means that you take x1 dot, expand it like, let's say Euler's method, you will take it to be x time t plus delta t minus x of t divided by delta t, and then move things around. And so it'll tell you how x t plus delta t is a function of x at t and u at t. And then you can keep doing that to get the system dynamics. Okay, okay, now that we have this form, let's talk a few things about this equation. If the equation is very helpful in figuring out if the system is stable or not. So check for stability. Check stability of uncontrolled system. That I mean, if there was no control, how would the system behave? And the way you can just check stability, just like we did for the walker going downhill, is if it's at its, if for the walker, if it is on that cycle which is stable, if you keep walking, not fall down. But if you perturb it, if it falls down, then you know it's unstable. Or if it doesn't fall down, it's stable. So in order to test the stability, you need to push the system somehow. So if you want to look at the system of the stability of the uncontrolled system, this is the uncontrolled system. And what you can do is you can perturb this numerically and then see how x dot evolves, and you sort of get some intuition, but there's an easier way to check for the stability of the system. It turns out that you need to compute the eigenvalues of A, just like the eigenvalues for that walker going downhill, but the eigenvalues are tested against a different condition. So compute eigenvalues and check if the real part is in the, so I should say check if all the real parts, because an eigenvalue can be imaginary, right? If you have a real part and imaginary part, are negative. If they are negative, then the system is stable. Okay, so very easy test because there are tools to compute the eigenvalues of a matrix such as A, and all the eigenvalues should be less than 0 or negative. Now, it sometimes does happen that the eigenvalues are not. So if the eigenvalues are not negative, not positive, but they are imaginary, so they lie on the if you've taken control class, they lie on the y-axis. In that case, the system is said to be neutrally stable, so it will not remove or add energy. So a spring mass system is neutrally stable because if you take a string mass system perturb, it will just keep wobbling around. It will not damp out, or the oscillation will not damp out the growth. So for this particular problem, what you expect is when you put these, when you put some numerical values to k's and m's, and you take the eigenvalues, you see that all the eigenvalues are imaginary, which means that system is neutrally stable. It will not become unstable or lose stability. Okay, so we'll do that check in a bit. Now, once you check this and you see that the system is either, let's say, uncontrollable, it is either unstable, or if you see that it may be stable, but it may not be reaching its equilibrium fast enough. So if you remember when we talked about under damped oscillations, the system is to oscillate and then go to 0, but that's too slow for us. We want it to go to 0 faster than that. And so you can actually use control to figure that out. We've done that in the past where we looked at the system, we linearized it, and then used the fact that we can always make it critically damped and get it to 0 fast as possible, which is one of the goals of control theory. Now, you can use control which is U, to either stabilize the system if it's not stable, or make it more stable. But I really mean you want it to push to 0 as fast as possible. Either push to 0 or push to whatever reference you want. Now, before you can do that, it turns out there's a condition you need to check. That's called controllability. However, one needs to check if the system is controllable. Have you heard of controllability before? How many of you have heard controllability before? Just 2 or 3. Okay. So this is really taught in a course. If you take 412, I think you'll be taught controllability. I'll define what it means, and I'll just give you an intuition, and then we can just move on. I'll tell you what condition to check for. So a linear system is controllable if and only if it can be transferred from any initial state x0 to any terminal state x of t within a finite time. So you know what, let me take this example. Let's take the Dubin's car. And this is the steering. And this is for speed control. Right, so what you have in a Dubin's car is, it's more like a bicycle where you use your, you pedal harder to get it to speed up. So there are two wheels behind. So think of a tricycle, and then you use the steering wheel in the front to steer. Now, what this definition says is, if this car is here, and if you want it to go to some other point, so this is at x of 0, and this is x of t, then if you can go from that state to another state in finite time, then the system is said to be controllable. It's not really talking about how much accelerations or how much speed you can achieve, how much steering you can achieve. It's very broad that you don't really have to consider about the limits on the speed and steering. Now, a case where it's maybe easier to understand this concept if you think, when would the system be uncontrollable? So let's say that I remove the steering from the system. Now I cannot steer, I can only go straight. In this case, if I want to go in 2-dimensional space to this point, I just cannot reach there because now the system can only travel straight. Now, if I'm pointing, if that goal is here, right, in the straight direction, yes, I can achieve that point. But then remember that this definition says to any terminal state. So since our state space is, our system is supposed to move in the XY plane, this is a special case, and this one is not a special case. It's like any point. So it cannot reach this point, but can reach this point if we remove the steering, and that means it's uncontrollable. Now, this system, if it was a, let's say, a tram or train, and it was going on a rail, and we know that the only thing we need perhaps the only thing we need in a train is to go straight, and the state space, or the space of locations is just on that rail, then yeah, that system is controllable because we have enough control authority to do that. So we need to check this condition for the system. And the way this is done is, without going too much into the theory, is we need to check for the rank of a particular matrix. It's called the controllability matrix. It's defined as A, n minus 1, B, n minus 2, n minus 3B, so on till A, B, B. Okay, what is n? N is the system DOF. So for example, in the example of spring mass tamper, so spring mass, we talked about n was 4. So we set up this matrix. We just need A's and B's, which we've already found out. We check the rank of C0. If it is equal to n, then system is controllable. And if rank of C0 is less than n, system is not controllable. Okay, what this rank really means is, what happens is when you assemble that matrix CO, you'll see that it is a 4x4 matrix, and the condition that the rank is n literally means that each row or column are independent of each other. And if they're not independent, then they're dependent, which means that the system is uncontrollable. It's something to do with the fact that the same thing which I showed with the example, which is if you have speed control, you can go one direction, but you cannot go in other directions. Or in other words, there are no solutions in that direction because this matrix doesn't really give you that opportunity to travel in lateral directions. Okay, so I don't want to go into details because there is a derivation and just not worth doing it. We'll just check this. Now, in Python, there is a module called control, pip install control. So do this in the terminal if you want the control. It's by default, it's not installed. Then you would import control. And then what you'll do is you'll say, you'll compute the controllability matrix CO as control.ctrb, where ctrb is the command in control to compute the controllability, and you just apply it with A and B. And then to compute the rank, it's basically NP, that's numpy, Linalg matrix rank of CO. Okay, so do that and you will have, it'll tell you the rank. And then once you know the rank, you can say if it's controllable or not controllable just by looking at N. Okay. Let me show you code first. And then we'll talk a little bit more about control, but let me show you how to do this in Python. Okay, I did a bunch of things, including the controller, but I'll show that in a bit. Okay, so I define case and I put some random numbers. I create A, create B. I use in Linalg, there is an eigenvalue command, which you can give you the eigenvalue. It gives the eigenvalue, eigenvectors. I'm only interested in the eigenvalues, and that will be printed by eigenval. And then it computes the controllability matrix and computes the rank. So if you run this, okay, I don't have, okay, so this something that I can do right now and show you how to do CMD install control. Okay, it's installed. You probably don't need to restart. Let's see. Okay, there it is. So it gave you eigenvalues, and now it's might be a little bit strange to see what the eigenvalues are because it gives a big number, but then shows 1e negative 17, which means it's 0, right? So the eigenvalue here is only this part, the imaginary part, 2.67. Again, it gives you this big number, it looks like a bigger, but it's actually 1e negative 17. So this is actually a negative eigenvalue. Here we have again E16, so 0, 0.91, and then minus 0.95. So there are 4 eigenvalues, and those 4 eigenvalues sit on the y-axis, imaginary axis, which means that the system is actually neutrally stable. However, when you control the controllability matrix, is controllable. That is, we can do whatever we want with the system. One is called pole placement. Okay, the idea here is we know that system is unstable if the poles are on the right half or on the imaginary axis. So we want to move them to the left half. So if you are able to move the poles to wherever we want them to move, then we can get the system to be stable. So this is pretty much placing the poles where we want. So what we do is we start off assuming U equals minus kx, where k is the gain matrix. Okay, so if you look at the equation, we have x dot equals ax plus bu. Sub in the value of u. We have ax minus bkx. I just put u equals minus kx. So we have x dot equals a minus bk times x. And now we can compute the poles of the system. So if you can compute the poles, you can judiciously choose k such that the poles are wherever we want them to be placed. So what we'll do is we'll place poles at some variable p, okay, which you will define. This is a user choice. Okay, so the way you do this is you can do a calculation, which I don't recommend. You can get this from the control module. You just say control dot place, and you supply it with A, B, and P. P is again a user choice. You define where you want the poles, and it will give you the gain k. Say place eigenvalues certain location. This location is P. Okay, so I'll show you the code how to do that. That's method one. Another method, which I would say is a better method than placing the poles or placing the eigenvalues, is using a linear quadratic controller. Okay, so what is a linear quadratic controller? So we have a system x dot equals ax plus bu. We try to compute u such that it minimizes a cost function. So it minimizes j, and j is given by x, ef, f, xdf plus, let me continue the new line, integral 0 to tf x transpose q x plus u transpose ru plus 2x transpose nu dt. Okay, so x and u is something you know. What is f, q, and r? So f, q, r, n are user chosen matrices. Okay, and they need to be of appropriate dimensions. Depending on x and u, you can figure out what the dimensions of q, r, and n are. F, the first part, which is out of the integral sign, is what is known as the terminal cost. What it means is at the end of time tf, that is t equals tf, you will be in some state, and that state has a cost. So you want to choose a state which is probably has very little cost. So f penalizes, depending on what x tends to be, it penalizes that final state. So if you don't want to penalize the terminal state, you just put f equals 0. Q, R, and N weigh the deviation versus the effort. So Q, for example, weights the state. So the smaller the x is, that is, the closer it is to 0, Q will, that part is going to give you very little contribution to J if it is close to 0 clearly. So the bigger you make Q, the system will try to find values of U such that X is as close as possible to U. Now that is by itself not very important unless you club it with R. So when you compute these Q, or when you set this Q and R, they are N, they're set relative to each other. If you make Q much bigger than R, then you will see that you will end up having more control. So what it will do is it will have a very aggressive control, maybe I should say aggressive control. And if Q is less than R, then you have less aggressive control. Because what's happening here is when R tends to be big, U will tend to be small, right? You can just look at that expression. When R is big, U tends to be small. If U is small, then it's less aggressive control, and vice versa. There's a cross term N, which I normally don't, I just put it equal to 0. But you can actually tune the cross weighting term between X and U. There are some conditions on Q and R. I think Q needs to be, and I may be wrong on this, positive, definite, and R can be semi-positive, definite. This means the eigenvalues should all be greater than 0. This means that eigenvalues can be greater than equal to 0. So first of all, it's a cost you're trying to minimize, so that cost should be positive. That's why Q and R should have some sense of being positive. And then R, you can actually make R 0. Some people just don't penalize R, which means the lower the R is, the more aggressive control is going to be. And so that kind of control tries to pretty much meet that expectation on X. Okay, so that's just a cost function. How do you solve this? Well, there's a whole derivation on how to compute the, okay, so before I do that, it turns out that the solution to this is similar to the solution of the pole placement. So there is a gain K, which comes out from solving this optimization. Now there's a derivation which goes in how to get that k, and that derivation is based on the fact that when you have a cost function and you're trying to optimize that, you take the first derivative of the cost function, but then there's an issue, which is you not only have to minimize the cost function, you also need to meet this constraint. So then they do what is known as a constraint optimization we've done before. You need to augment that cost function with that equation. There is a method called, it's basically similar to Lagrangian method we talked about, but then you take that, you take the first derivative, you with respect to XTF, XU, and then the Lagrange multiplier, and then you get 4 conditions, and then based on those 4 conditions gives you a solution which will give you the value of k. So let me just, I won't derive it, it's no point in deriving it, but I just write a few things down. The solution is something like this: R inverse B transpose P plus N transpose. So K is the gain, remember? And that K is R inverse B transpose P plus NP. Now B we know, N we don't know what P is. P is, in order to solve for P, you need to solve this equation. This is where it gets really complicated. A transpose P plus PA minus PB plus N R inverse P transpose P plus N transpose equals 0. Oh, sorry, plus Q equals 0. Okay, so this equation is kind of famous in control worlds, called Riccati differential equation. Now, how will you solve a differential equation if you don't have, it's like an ODE, right? How do you solve it without initial condition? It turns out there is a boundary condition to it. So what normally when you have a differential equation, you specify what happens at time t equals 0, but here you're given what happens at to p at time t equals tf. And so in order to get this equation, you need to integrate it backwards, or you can integrate it forward. So you'll assume some value for p at t0 and integrate it forward. Okay, so what people do is, if you want to solve this problem, you need to solve this equation every single instant of time. For example, if the system is linear, then you can just solve it once and you're good, you're done. But if you have a system where A and B varies as a function of time, then each time you need to solve this equation, and it takes a lot of time. So what people do is they solve for a special case of this problem. So they always look at a special case, and that special case comes when instead of looking at the finite time cost, they look at the infinite time cost. So they drop the terminal cost, because when you have infinite time, you're really not bothered about what happened in the end, because we don't know what's going to happen at infinity. And then we specify this cost, which is exactly the same, except with the integral being, which goes from 0 to infinity. So this is the what is known as the infinite horizon problem. Its solution is also E equals minus kx, and you have the same K matrix. So what's simpler is that instead of having a differential equation like I wrote down there, you don't have a differential equation. You have a steady state form of the differential equation. The steady state form is when things are steady, which means that the rate of change is 0. So P dot is 0. So we have AP plus PA minus PV plus N times R inverse P transpose P plus N transpose plus Q equals 0. This is the steady state Riccati equation. Okay, so will not really solve this. What we'll do is we'll basically use the the controls module and get the gain K. So if you use this command, KPE equals control dot LQR and supply it with A, P, Q, R, N, and N can be 0, as I said, R can be 0. So at the minimum, you need to supply A, B, and Q. Then it will give you the gain, the solution to Riccati equation, and then this will give you the eigenvalues. Of closed loop system, which is A minus PK. The eigenvalues of this. Okay, so I wrote down all these things just so that you understand the theory. It's not like just use it. Just remember that you're solving this special case when you're doing LQR, which is pretty much what everybody does. But then there's this other thing, which is this non-steady state, which is more complicated, and you need to solve a more complicated problem there. So the last thing I want to tell before we take off for today is that you can do that in Python by using this code. Okay, so I already computed the controllability matrix. I saw it's controllable. I can do pole placement. Here poles, I just decided I'm going to put the poles at -1, -2, -3, -4. So I call the place command. It will compute. It'll give me the gain K. I can also check for the eigenvalues by doing A minus BK. That's what I've done here. It's a bit complicated than it would be in some other programming like MATLAB. And then it print the eigenvalues. And then I have LQR, which now this is a 4x4 system, so Q should be 4x4. R, I've put identity times 1e negative 2. So this is how I can weigh in Q with relative to R by putting a suitable weight. So if I put -5, for example, you will have more aggressive control. So the smaller it gets, the more aggressive it gets in terms of control. I gave K as C. S is the same as P. And so running this code. Okay, so this is pole placement controller. So you can see that the gain is 2 rows, 4 columns, because it needs to be multiplied with X. X is 4 cross 1, but then there should be 2 rows because there are 2 controls, U1 and U2. Eigenvalues are as I was promised, -1, -4, -2, -3. I just by manually checking them. Then I do the LQR. It throws up different gains. So these gains you can see are different from these gains. When I try to compute the eigenvalues, in this case, I think the eigenvalues are part of the calculation. Give me the eigenvalues. So I just printed those out. It's -15, -5, -1, -1. Now, if you don't like this, then what you can do is you can go back and change these Q and R. For example, if you change this to -4 and run it, you get the gains, you can see have increased because it's more aggressive now. And the eigenvalues is -161, -61, -1, -1. So you see that the gains, these 2 eigenvalues are far away from the origin, 0, 0. I thought it was interesting that these 2 eigenvalues don't change. I don't know if it's possible to move them. I think we always have 1,600. It's interesting. I don't know why you cannot change those. Now this need not be this. You can actually weigh it differently. So I have put 1, 1, 1 on the diagonal, but you could have different values on the diagonal. What people normally do is, remember that Q it weighs the state. So x has the positions of the two masses and then the velocity. So one way of scaling this is they will divide the position by the maximum value. For the first two rows, the first two ones would be scaled by the maximum distance moved by the first two blocks. The second, the third and fourth would be the velocity. So you scale it by the maximum velocity, and that way you can weigh it equally. So there's this whole issue of scaling this properly. And I just used something, but you might have to change it. I just don't know why you cannot change this. Seems like you could change them here, but not quite there. And there's something I need to look at. Okay. I think it's to do with this Q and R, because
so the cost of it's the cost function increases so dramatically with scaling the velocities that the solution will never.
Right. Yeah. So I think you can fix it, because here's the example. I put -10, -20, -30, -40, and I get gains and I get this. So clearly I have to do more work with respect to the scaling, because this is saying it's possible. I mean, in general, think of it this way. There are 4 equations, 4 things to place. I would imagine that the system is not ill-conditioned, that you cannot do what you want with such a system. So it should be possible to put the poles wherever you want, like I've done with pole placement. Okay, we'll stop. Next time we'll do linearization, which will extend it to nonlinear system. Computes the LQR gain, okay? And then I made a simulation with this gain. So here the problem is if you perturb the system, okay, so in this case, remember there are 4 state variables, positions of the 2 masses and the velocity. So the position is the first 2, next 2 are the velocities. So if you perturb the position of mass 1 to 0.5, and you don't do you apply any control, so the control U is 0, then what happens? So I just use ODE integration to integrate the equations, and what comes out is plots showing position, velocity of, I think both links are there. You can see that it's like a sinusoid, pretty much that the fact that if you start at 0.5, it just keeps wobbling at 0.5, that's what happens. Now what I did next was I took the gains. This is the gain which came from this earlier code, this gain, and I copy pasted it here. And now I learned the system with this control system, and you see that it actually starts at 0.5, damps out to 0, and velocity goes to -0.5, damps to 0. So the gain is doing its job of stabilizing the system or placing the eigenvalues wherever you want. So that's what control does for you.